Hello and welcome. I'm Simon Pukrop, and today I'm going to present to you our paper on server cloud scheduling. This was joint work together with Martin Mark and Friedhelm Meyer auf der Heide. We all three come from the University of Paderborn in Germany. Let's jump right in. First, what is server cloud scheduling? First, on motivation. Let's imagine that you are hosting a small website or something like that, and usually you have low traffic, which is handled by your own server. But occasionally there might be traffic spikes, and then the question becomes, well, what do you do with those traffic spikes and with the additional load that you can't handle? And in today's day and age, the answer to that question mostly is rent cloud time, with services like Microsoft Azure or Amazon Web Services. To have this scalable isn't really a problem anymore. And we will make the following assumption on this type of problem. You have an own server, which is free of charge, but is only one machine. Then you have a cloud, which costs money, but has unlimited machines. And then you have, whenever you have communication between those two environments, that needs additional time. To go into a bit more details on the model, of course, we have a scheduling problem. So we have a set of jobs, which is in this case given as a task graph with a singular source and a singular sink. And each job has processing time PS on the server and PC on the cloud. And as I said, you have one owned machine, which is the server, and an unlimited number of rentable machines, which is the cloud. And then we have the edges of the task graph as precedence constraints, and those also inhabit some communication delay C, which is always invoked whenever we switch between one machine environment and the other. So we have, let's say we have some job which we process on the cloud, and then we process the following job on the server, then you have the communication delay between those two. Okay, and then as is typical with scheduling problems, well, the task is to schedule the task graph, and we have two different objective functions for that. One is, well, you have a deadline D, and you have to minimize the cost to schedule this, and the other is basically just the other way around. So you have given a budget B, and you have to minimize the make span. Okay, we have three different types of task graph that we looked at in our research, one being chain graphs, which I think everyone knows. Then the next one is a fully parallel graph. There we still have our source in the sink, but besides those two, everything is just in parallel and not dependent on each other. And well, the last kind is just a general graph. So we have a source in a sink, we have a directed acyclic graph, but everything else can look whatever it wants to look like. Now I want to give you an overview over some of the results of our paper. And let's start with the unit case results. So we have a unit processing time variant here, where every processing time PS is equal to PC is equal to 1 for every job. And we still have precedence constraints, but all the communication delays are 0. And this is in fact trivial for both our objective functions. Both of them lie in P. So we have simple greedy algorithms which follows along optimally in polynomial time. We already make this a lot more interesting if we also include the communication delays. In both objective functions, we jump from the problem in P to a strongly NP-hard problem. This is what I want to give you a few more details on later in the talk. On the constructive side, for the minimization of cost, we also have a 1 plus epsilon divided by 2 epsilon approximation algorithm, but that needs resource augmentation on the deadline of 1 plus epsilon times the deadline. Okay, then we looked at different task graphs. So we have fully parallel graphs and chain graphs, and communication delay of 0. And this is weakly NP-hard for both of our objective functions. And for both of the objective functions on the constructive side, we also have F-Peters results. The F-Peters results also hold for the chain graph case when the communication delay is arbitrary. Okay, then we moved to arbitrary processing times, arbitrary communication delays, and more or less arbitrary task graphs. And what we have here is this one with a constant maximum cardinality, source, and sink dividing cut. Okay, so what is this? Let's imagine that you have the task graph here, and you have your source, and you have your sink. And yet now you divide them into two sets, or you make a partition of them, and one of those has to contain the source and the other has to contain the sink. And you may have edges in one of them, you may have edges in the other of them, and you may have edges going from the source containing one to the sink containing set, but not the other way around. Now you just simply count the number of edges that goes between those two sets, and the maximum number of edges that you can find in any given task graph is this maximum cardinality, source, and sink dividing cut. Now, if that is constant, we can, for the minimization of cost, give an optimal solution, but again, with resource augmentation of 1 plus epsilon times the deadline. For the minimization of make span, we even get an FPTS. But in that case, we have to be a bit more involved in the algorithm. The last one we looked at is a general problem. There we looked at the minimization of cost and could basically adapt the reduction of the unit case to make it so that we can show that there is no approximation possible. Why that is so, I will give you a few more hints about later. Okay, so again, in the following part of the talk, I want to talk about the unit server cloud problem, because the step towards general graphs is quite large. So what we have now is arbitrary task graphs, but every processing time is equal to 1. And that is true on both the server and the cloud. So they are speed-wise identical machines, but the difference between those is still given by the server being one free machine and the cloud costing you money and being usable in parallel. And every communication delay here is 1. And then the question becomes, is it still hard? And as I said before, if the communication delay would be 0, this is trivial. The slice and peony can simply solve it greedily. But with the one where the communication delay is 1, it's in fact hard. Okay, so I want to give you an intuition on the reduction before I jump into the details. And we want to reduce that to the unit server cloud problem, and we will use the decision variant of this problem. So basically, is there a schedule with make span smaller or equal to the deadline and cost smaller or equal to the budget? And the general idea here is we limit the number of slots where jobs even fit on the server, and all of them have to be filled up with jobs on the server to hit our budget restraint. And we will have 2 jobs per variable, and one of them is a true assignment, one is a false assignment. Basically, we have something like X and not X, and one of them have to be put on the server, the other one has to be put on the cloud. One of them will stand for the true assignment, the other for the false assignment. Then for every clause, we will have for every literal a concurrent job. Only one of them can be placed on the server, and only if it is truly assigned. And then we can basically only hit the budget restraint if for every clause one variable is true, and for every variable one of the assignments is on the server. We have 2 problems here. The first being that we basically have no memory in this problem, because we want to divide stuff by putting it on the server or putting it on the cloud. But after one time step, we basically lose memory of a job's location, because the communication delays can just happen concurrently. And since they are always just 1, after one time step, we basically lose information where anything was. So we somehow have to have some idea to relay decisions on assignments. And the second problem is that we have to somehow force most of the jobs onto the cloud for the other ideas didn't work. We first tackled the second problem with a gadget that we call the anchor chain. The anchor chain are basically two braided chains which happen concurrently, and they have lengths roughly equal to the deadline of the whole scheduling problem. And then the idea is that all the jobs of this anchor chain have to be placed on the cloud, because if we put something on the server, either we put multiple things on the server, but then those have to be done in series, which will go over the deadline restriction that we have, or we put only single ones of them on the server, but that would invoke additional communication delays, which would also get us over the deadline restriction. So we basically have this chain. Everything on it is on the cloud. We have fixed time steps, which I wrote in this example over them, and we know in a specific time step this specific job will be processed on the cloud, and we will later use this to hook our other gadgets onto them and to give them a structure. The next of these gadgets being the variable gadget. As I already mentioned, for a variable x we would have x and not x, and both of them are connected to the anchor chain. And with just that much flex that we can place one of them on the server using one of the 3 time steps we basically have to do the communication delay back to the server, process it on the server, and do the communication delay back to the cloud. And the other of the jobs, of course, just has to be placed on the cloud. The job on the cloud is what we will later use as a true assignment. And here we use that this one finishes a time step early, because that one doesn't have to do a communication delay. Of course, we could also do just both on the cloud, which translated would basically mean that x and not x are both true. But in that case, we wouldn't fill one of the slots with a job on the server, and we wouldn't hit our budget restraint in the end. Okay, and then we have the clause gadgets, and here again we have one clause job, this C, and for every literal in the clause we also have a job that is connected to the clause job. So here in this case we have x, not y, and z. And since the timing of the clause job C is fixed via the anchor chain, we have specific timings in which x, not y, and z have to finish at the latest. And that is one time step later if they are done on the cloud, or one time step earlier if they are done on the server. So it's basically harder to put them on the server. That is what we later use. Okay, so we have the variable gadgets and we have the clause gadgets, but they are not connected by now. So this is what we want to do here. We have this connection gadget. And basically the connection gadget is a chain of jobs with one time step flex. So in our example here, we have 4 time steps on the anchor chain, and the chain is only 3 jobs long. So we have one time step flex where we can shift it to the end or to the front. It is also connected to the variable job and the corresponding literal job. Okay, now comes the information on why does this do anything. As I said earlier, when we have the variable job and we put it on the cloud, that basically means that it is true. And as I also said, that means that we can put it, or that we can finish processing it one time step earlier. And since we could finish processing this one time step earlier, we also can start processing the connection chain one time step earlier. And by doing this, we get one additional time step of flexibility in the end for the literal job before the clause job. And so we can use one time step to send information to the server, do our literal job on the server, and do the communication back to the clause job. If our variable job would not be true, so it was processed on the server, Then we have an additional time step which basically shifts the connection chain one time step towards the clause gadget. And that means that there is not enough time anymore to do this communication to the server, processing the job on the server, communication back to the cloud. So here we have to process the literal job of the clause gadget on the cloud. Okay, so if we connect all of these constructions, what we basically have is as a big rectangular at the top, the anchor chain, and then cascadingly we have the variable jobs, and also cascadingly we have the clause jobs. And we have connected them via these connection gadgets, connection chains. And basically now the idea is that every one of these pink rectangulars that I've painted in here has to have exactly one job on the server. Otherwise, we don't hit our budget. So that means that for X, we have to decide X or not X has to be true. For Y, we have to decide Y or not Y. One of them has to be true, and so on. And for every clause, at least one of the variables of the literals has to be satisfied. Otherwise, we couldn't put the respective job on the server. And what this means basically is that there is this schedule that hits both the deadline and the budget restrictions if and only if there is a satisfying assignment for our Boolean formula. Okay, a few words, as I mentioned, on the non-unit version of this problem. Basically, we can do a roughly similar reduction. So the idea is the same. We have an anchor chain, we have these variable gadgets, we have the clause gadgets, we have connection gadgets. And the main part that we change is that we remove time spent on the cloud by what I call busy waiting on communications. So we spend time only by having chains of jobs which have to switch basically from server to cloud, from server to cloud, from server to cloud, and always forcing communication delays between those, which means that we can force arbitrary communication delays or arbitrary wait times without putting anything actually on the cloud. And by doing this in a clever way, we can degenerate the problem in a way that we have a satisfying assignment has costs of exactly 0, and a not satisfying assignment has costs of 1 or some constant c. And basically now we just have a Boolean problem, which just has a correct assignment with cost 0 and a not correct one with cost 1. And I think it should be easy to see why there is no constant factor or approximation or something like that possible. Okay, that was it for my talk. Thank you all very much for listening to me. And if you have any questions, feel free to ask. Thank you again.